Welcome back to the Explainer. Today, we are taking a bit of a journey. Specifically, we're mapping out the journey of a packet. If you've ever felt completely bogged down in the weeds of hardware verification, well, you're absolutely in the right place. We're going to demystify the core building block of communication in the universal verification methodology, the transaction.
Okay, let's dive into this. Have you ever wondered how modern test benches avoid the agonizing, soul-crushing process of toggling individual wires clock by clock just to send a single piece of data? I mean, in the old days, hardware verification literally meant manually wrangling pin-level signals. It was tedious, prone to errors, and just incredibly slow. But to verify today's massive, complex chips, we really need a much more abstract and much faster solution.
And that solution is transactional-level modeling, or TLM, and its fundamental vehicle, the UVM sequence item. TLM lets us abstract those low-level 0 and 1 signals into neat object-oriented data packages. You can kind of think of the UVM sequence item as the DNA of your test bench. It allows us to bundle information together and move it across our entire environment at a much higher, much more efficient level.
So, here's our roadmap for today. First, we'll meet the UVM transaction. Then, break down the anatomy of a packet, look at constraints and randomization, move on to creation and printing, and finally, track the full transaction lifecycle.
All right, Part 1. Meet the UVM transaction, the foundation of communication.
To really grasp this, we have to ground ourselves in the UVM base class library outlined in the IEEE 1800.2 standard. We need to understand the difference between the base classes. We've got our static components extending from UVM component. These are things like your drivers and monitors. Think of them as the physical buildings in your testbench city. They're built once and stay put for the whole simulation. Then we have our dynamic objects, extending from UVM object, which handle core data operations. Now, a UVM transaction inherits from UVM object, but adds a really crucial timing and recording interface. So if components are the buildings, our transactions are the cars constantly driving on the roads between them.
Moving on to Part 2. Anatomy of a packet, building the blueprint. I always like to think of a transaction just like a physical piece of mail traversing a postal system. Think about what a physical letter needs to get delivered and actually be useful to the person opening it. It needs an address, right? That's your destination. It needs data, which is the actual letter or the contents inside the envelope, and often it needs a command or write instruction, which tells the recipient exactly how to handle it once it arrives. A network packet in a UVM environment requires these exact same properties.
And this brilliantly illustrates how those physical packet concepts translate directly into SystemVerilog class properties. In the code, we extend the UVM_transaction base class to create our custom trans class. We define our fields with the rand keyword, a random integer for the address, a random integer for the data, and a random bit for the write instruction. Boom, we've just built the structural blueprint for our mail. Now notice that rand keyword? That is absolutely crucial for what we need to do next.
Which brings us to Part 3, constraints and randomization, setting the rules.
We obviously don't want to just send the exact same packet over and over again. That wouldn't really test anything. We want to stress test our design with varied stimulus. By using that rand keyword, we're telling the simulator to generate random values for our address and data fields. But wait, completely random data? Actually, scratch that. Purely unbounded random data is a terrible idea because it can cause immediate, useless errors if it hits invalid addresses in our device memory. So we must apply constraints. We define an address range constraint block to make sure our randomized address is always between 10 and 20. And we do the exact same thing for our data range, keeping it strictly between 100 and 200. This makes sure our payloads stay within valid testable parameters while still giving us that rich, unpredictable stimulus our verification process thrives on.
All right, Part 4, creation and printing, the spark of life and a voice.
Now, what's really interesting about this next step is how we actually spawn these objects into our simulation environment, and just as importantly, how we keep tabs on them. There's a pretty stark contrast between basic object creation and the preferred UVM factory pattern. In standard SystemVerilog, you might just call t equals new. Super simple, right? But in UVM, we strongly prefer using the factory, calling type_id.create. Why go through the extra typing? Because the UVM factory allows us to override object types during simulation, right from the top level, without touching the original component code at all. It gives our test bench massive, game-changing flexibility for future reuse.
So, once it's created and filled with random data, our transaction needs a voice. As verification engineers, we stare at simulation logs all day long. If a transaction just prints out its raw memory pointer, it's literally useless to us. So, we implement the convert-to-string virtual function. By using the $formatFstring formatting method, we can organize our address and data properties into a nice, readable string. This gives our packet a clear, human-readable voice when it's tracked in the logs.
And here is the proof. When we pass that generated string into a standard UVM_info macro, we get a beautiful console output exactly like this. Sending address equals 11, data equals 11. It proves to you that your formatting code is working perfectly. And believe me, having this readable output makes debugging 1,000 times easier than staring at an endless wall of raw hex dumps at 2 a.m. when you're trying to track thousands of these packets flying around.
Finally, Part 5, the transaction lifecycle moving through the test bench.
Okay, we have our customized packet fully built. Now let's watch how it actually travels. During the very time-consuming UVM run phase, a transaction goes through 4 distinct chronological steps. First, creation, using that factory create method we just discussed. Second, we call the randomize method to populate its fields safely based on our constraints. Third, we transmit the transaction across the test bench using a method like put or get. And finally, the transaction is extracted and checked by a component, usually a scoreboard, to verify if the design behaved as we expected.
Let's look at how this builds our communication plumbing network. To move our packet from a producer to a consumer, we rely on 3 key pieces of TLM routing terminology. A port is the initiator. It essentially requires the connection to initiate a transaction request. An export is a forwarding mechanism, passing the interface down through the component hierarchy. And an IMP, short for implementation port, well, that's the ultimate target that provides the actual task execution.
So here's where the rubber meets the road in the code. The producer calls out .put, taking our beautifully constructed randomized packet and shoving it into the network. Simultaneously, the consumer catches it by executing its put task. This is the exact moment the packet successfully bridges the gap, leaving the producer and being caught by the consumer without either component needing to know the hard-coded path of the other. It's just brilliant, decoupled communication.
We've successfully abstracted messy signal wiggles into elegant, self-contained data packets that can route anywhere. But this brings up a really fascinating question for you to ponder. How might you sequence thousands or even millions of these individual transactions together to rigorously stress test a massively complex system-on-chip design? Well, that is exactly where UVM sequencers come into play, and it's what we'll be exploring next time. Thanks for hanging out with me on this explainer. Keep experimenting